Check, check. Check.
Okay. Good morning, everybody. Morning. Okay. Today we will start again our summer course in 4th day. And today I am Valen and
Fabiola.
yeah, okay. We are the master ceremony for today, and
The first session is Orthogonal Matrices and Applications. It will be delivered by Dr. Lin Sok from School Mathematical Sciences Anhui University. For Dr. Lin Sok, time is yours.
Thank you. It's my pleasure to see you again here in the morning session. The title of my talk for this morning is about orthogonal matrices and their application. And outline is the following. I will start talking about orthogonal group. First, I will consider for binary case, and then generalize to arbitrary case. The generator of the group will be given in this talk, and as application we construct some two important subclass of linear code. The first one is self-dual code that many of the speakers mentioned many times. The second one is about the construction of linear complementary dual code that I will define later. And I will show the connection of the orthogonal group and the so-called self-dual band function. And we use an orthogonal group to classify the so-called self-dual band function. So now let us start. Here is the definition of orthogonal group. It's a subgroup of general linear group of index n, such that the element satisfying condition A times A transpose is identity matrix. And for notation for Q equal 2, we just write simply ON. So the order of orthogonal group over FQ is known long time ago, since 1969, and it is determined as follows. You have, when the characteristic of the field is even, then you have these two cases, and when sorry, not characteristic, but I mean when Q, yes, we can also say characteristic is even, and here when Q is odd, I mean here we have two cases, and for the second one we have three cases. It is determined by Mark William. To generate the orthogonal group, we need some. Here we are working in the subgroup of general linear group. Then we need some transvection here. Is a linear map from F2 to the n to F2 to the n, defined by this rule. And this is called transvection. You can check if this map is linear. and it will satisfy some property. Let me recall some fact about this transaction. You take a vector u of Hamming way even, but for some easy treatment, I may just take the Hamming way of u equal 4, but you can take any even Hamming way for vector u, and then you give this rule to the map, and it can be easily check that this is linear. This is the property that you can do calculation by hand, that Tu is an orthogonal matrix. It means that Tu times Tu transpose is nothing but identity matrix. You can check it by yourself. And when you take the product of Tu with itself, it's identity matrix. This shows that this matrix is symmetric, right? Because the first condition you have Tu times Tu transpose identity matrix, and here you have Tu square identity matrix. It means that Tu equal Tu transpose, so it is a symmetric matrix. And if you have this condition, then the operator is commutative. And if you take any element in the orthogonal group and you get this equality. So here, if you have some vector v in f q to the n, which is perpendicular to u, then you have v times Tu is v. This is a very important ingredient to generate orthogonal group. But let me go back a bit to orthogonal group here. You have A times A transpose identity matrix. Can you give me some matrix which satisfy this condition? Yes, of course. Thank you. So, if you consider permutation matrix, how many possible permutations? I think it's if you take index n, then it must be factorial of n, right? So maybe you can just do some here. It's not difficult to check that the number of permutation matrix is factorial of n. I mean, if you take n equal 3, or maybe I can start from n equal 2. Then you have here you have identity matrix, and the other one is yeah. I prefer to write 1, 0. Oh, okay. Then I think in this case you are applying some permutation map. And what about n equals 3? I think maybe you just apply something like 1, 2, 3 here, and then the first case is identity matrix, that we call it C0. And then the next one is C1, which is you consider some transposition. Transposition means here you take, you fix a sum here, and this is just 1 sent to 2, 2 to 1, and so on. And then you have another permutation. I mean, so in total is you can enumerate by yourself. It's 6. And then I mean here is nothing but just a representation of this. Okay. So I think if you have this feeling, then orthogonal, I mean permutation group. I mean the set of permutation matrix of index n must be subgroup of orthogonal group, right? Because when you apply the rule, it's like it satisfies the orthogonal condition, and then this is the other. I mean the subgroup of orthogonal group. So the when you look at the order of the orthogonal group, then it must be larger than the order of permutation group, right? So I mean the order of permutation is a factor of n. Now when n get larger, you may imagine that this group is larger, but this is just subgroup. So the group of orthogonal matrices is that I mean much bigger than the permutation group. So in 2007, Janus gave the following generation theorem for Q equal 2, and the theorem is as follows. For 1 less than n, less than or equal to n, or n less than or equal to 3, then as you have seen, you can verify by hand. It's exactly the group of m times n permutation matrix. And for n greater than or equal to 4, this group is generated by the transaction Tu and the permutation group Tn. If you want to look at the proof, you can go to I mean the reference. But to gain more time, I just want to do something and then maybe give some application. For the rest, you can read by yourself. And this is the work of Janus. And later on, I try, because of the motivation from the so-called LCD code, then I try to generalize it in, non-binary case, that we consider Q is different from 2, that I will give the generation theorem in the next slide. So one more thing about permutation group. In fact, in algebra, it is proved that this permutation group will be, is generated by all the transposition, right? And one more thing about, you can also prove that permutation group is generated by one transposition and one cycle of length n. Then to generate this orthogonal group, you need three generators. One is the transposition. Second one is cycle of length n. And the last one is the transvection TU. So here I calculate the other group by magma and also by the Mark-Williams formula. And just look at the size of the group together. You see here from n equal 8, I think we cannot reach all the elements in the group, right? 7 is okay, just 1 million. And this is the matrix of 7 times 7, so you can calculate the bit, and then you can also get the capacity, the space of memory storage. When n equal 8, it's still, maybe with some powerful computer you can still store the, but maybe for n equal 9 and 10, it's hopeless for visit all the elements, right? But in the next slide, we saw how to use this matrix to construct self-dual code. Because in the previous section, we mentioned about self-dual code that people try to construct from cyclic code, from many different point of view. But from my point of view, orthogonal matrix is a good candidate. So why, maybe it's like this is a motivation to why most people consider self-dual code. You may think about group theory, something like an automorphism group. That send code, some code to another code, which preserve Hamming distance. In that case, it's nothing but just permutation, because permutation will just send one code to other code by some shift position. Then the Hamming distance will not change. It means that two equivalent code will have the same capacity of error correction. I think in the first section we mentioned about the capacity of error correction, right? It's depend on the Hamming distance, and if you apply permutation group, then it means that it preserves the Hamming way, and then the capacity, the code will have the same capacity of error correction. And you may know Lattices Theory is you have both with module, and you can construct some the so-called unimodular lattices. When you have lattices, you have gram matrix, then unimodular lattice is nothing but just the determinant of the gram matrix is something which is in one rather than yes. And then we have some design series. The block design, T design, and also in invariant theory, which plays important role in a way enumerator of self-dual code. But I will show you in the next slide. Oh, I should say something about this. This is known. This was studied by Slow that self-dual code is asymptotically good. For application, you cannot use shorter code. You need a longer code. The length can go to infinity. But it was proved that self-dual code is asymptotically good. It means that when the length goes to infinity, the relative distance and the rate, the product of these two two things is always greater than 0. I mean, in real application, you can, I mean, a code with rate 0 is not interesting, right? And code with relative minimum distance 0, it correct 0 error, detect 0, I mean, error also. So it makes no sense. I mean, it's not useful. So you need to consider some code which has both rate and relative minimum distance positive. Otherwise, it's not so useful for application. And the way is sparse. I mean, you have a lot of zero-way distribution, and you may remember the for the magma session. I asked you to give, maybe not yet. Yeah, the Hamming code. For the Hamming code, you have of length 8 and dimension 4. It is a unique code up to equivalent, and it is cellular. And if you look at the way distribution is sparse, you have one code word of base 0, and I think it's something like 14 code word of way 4, and one code word of way 8. So you have only 3 possible way. It means that for the other way it's just 0. I mean, the number of code word of other way is just 0. So here some important fact about binary cellular code is by definition here is you have C and C pub, which is subspace of F2 to the n. And then here you have this condition. When this is just a subset, then we call it self-orthogonal and equal when. So it can be easily proved that from linear algebra, you have the dimension of C plus dimension of C pub is nothing but n, right? So if you get this condition, it means that you have k plus n minus k is just I mean the length. So n must be even. And here we call C equivalent to C prime if we apply the permutation rule P to C prime. I mean, we apply the permutation rule to the coordinate position. If it resolves, then the code is equivalent. And as I just said, permutation code will give the same capacity of error correction. Now look at the standard systematic form of the generator matrix. I mean, up to equivalent, we can bring generator matrix of the code to this form, right? You have I, and we can divide into 2 blocks. The first block is identity matrix, and second block is the matrix M. But if you apply, you can check that C is self-dual. I mean, you could consider parity check matrix, and here you take a generator matrix, and you can also consider parity check matrix. When these are the same, then the generator matrix and parity check matrix is nothing but just, I mean, they are the same. And then if you check the condition that the generator matrix time parity check matrix transpose equal 0, then you get this identity. And if we are not confused and if we are correct, this is what? What is M? I think it's an orthogonal matrix, right? It's the element in the orthogonal group. We call it orthogonal matrix. So now, can you? I think for constructing self-dual code, it's very simple. You just attach matrix identity with orthogonal matrix. Then you get serial code, right? If we have some way to generate orthogonal matrix, then serial code will be constructed. Even the group, the size of group is larger, but by magma you can use a random program, you can use a random command, then you can still construct. I mean, even the size of the group is still large. And as I mentioned, maybe the performance of random code is also good, but I don't know the proof, but it's like from my construction, it's like we can get a lot of optimal code. So here are some definition of type 1 and type 2 code. We talk about type 1 and type 2 for event characteristics. And here the code is type 2 when all the Hamming weight of the code word is a multiple of 4. And it is called type 1 if there are some Hamming weight of code word of weight can go into 2 modulo 4. Maybe I go back to this. Here, some fact about this you can check. When it is a such orthogonal, then when you take x times, the Euclidean product of x, then you get something which is x again. When you consider Hamming weight, it's nothing but just the rational sum of its coordinate. And then it must be even because here you have orthogonal condition. So when this is serial, then the weight is even, but it doesn't say that the weight is multiple of 4. It's either coming to 0 modulo 4 or 2 modulo 4. And one more thing about this code is this vector is always in C. Because you have length here n, and you can check that this is always you can check here because this even, then it must be orthogonal to this, so this must be in C. You can check this by using the second condition. So this is example of serial code, and here I just write in the systematic form, but I think you can get this easily with our cyclic code that we ran in Magma a few days ago by extending the coordinate. We start from 7, 4, 3. And then when we extend the coordinate, you get this guy. And you can check the way distribution is, you can test it is serial, and the way you only have 3 possible way. So here you have G is generative matrix, and here you have 2 parts, identity matrix and M, and you can check that this is exactly a orthogonal matrix. When you take the scalar product of the first 2 rows, what do you get? I think 1 plus 1, right? And 1 plus 1 modulo 2 is 0. The same happened to this. And this is equivalent to the extending Hamming code. Hamming code is a cyclic code generated by some polynomial. So this is the code word of wave 4. You have 14 code word of wave 4. But what I want to show you here is that this code word will have property of T design. Here is a 14 code word, and here I will not go into detail, but just give some connection that if we have T and V lambda design, the difference in T lambda is like the set of block. The set of point, and you have block, and every lambda block is contained in exactly every T point is contained in exactly lambda block. Here, if you look at the 3 points, 1, 3, 5. Here, when we are considering P here, the size of P is 8, and we have the block of size 4. And you may see that every 3 points is contained in only one block. For example, 1, 3, 5. Can you find any 1, 3, 5 in other block? No, just one. And the same for other. This is just connection, but people may in combinatoric maybe can develop more. But it's like you can construct P design from cell-dual code. So now the one important tool in studying code is the way enumerator. Why? Because the way enumerator is like a polynomial, homogeneous polynomial of with 2 variables, and it gives information about the number of code words of Hamming way 0 up to n. Then, if you have information about the way enumerator, then it's like you have the information about Hamming distance. Then it also characterizes the capacity of error correction. And the way enumerator of a linear code C of length n, is defined in this way. You have 2 polynomial, homogeneous polynomial in x and y. Then I think if you regroup all the code word of a you regroup the number of code word 0, code word 1. Then you can write the way enumerator in this form. And here what AI see here is the number of code word of AI in C, which is the way distribution of the linear code. And I think even in Magma you can also get this way distribution, right? You have information. If if you have linear code, then Magma can help you to calculate the way distribution, and you can get not just a minimum distance, but you can get all the information about the code word. So if there is no ambiguity, then we can write something just like this by omitting C. So as I mentioned at the beginning, you have something like a 1 is always in the code word, and since the code is linear, you have, if 1 is code word, then 1 plus x is also code word, right? Then here you have some like some symmetric. If you have I, and then ni is the same. Why? Because if you have, because cellular code contains 1, and since it's linear, when you take any code word C, then 1 plus 6 is also code word. And the Hamming weight of 1 plus C is nothing but n minus Hamming weight of x here, or C. So you have this relation. One more. Sorry. Here is the famous theorem by Asmussen. People working in combinatoric, but it can be related to linear code. Here you have C, binary linear code, and you have C perp. It's dual, but here it's not restricted to self dual. It's just general linear code, and we will use the notation that AI is the weight distribution of C, and AI perp the weight distribution of its dual. Then if you fix some parameter T and D, and you let some S be the number of I with this condition, then I mean a whole, I mean the code C will whole design. As I mentioned to you, that even Hamming code also contain I mean 3 design. So this is just an application, but if you want to, I mean the result, it's not easy to prove the result, because it's like you go from combinatoric to. So up to now you have seen that there are a lot of connections between coding, lattice, combinatoric, Boolean function, etc. Here, this Mark-Williams identity is very famous. That when you study code, even over ring, people will try to check that if the code hold. I mean, if the Mark-Williams identity also hold for code over ring, and if you consider Frobenius, then it always holds, but for non-Frobenius ring, it may be hopeless. You see, here, it says something about invariant theory. You apply some map here, but you still get something here. It's invariant. Here, the main equality for linear code in general. But if you take, if you consider self-dual, you have this situation. And if before the arrival of the shadow, some coding people give a lot of wrong result. They say that this code exists, but some shadow code exists, but it's like there is no way to check it. And in 1990, Sloan introduced the so-called shadow, which is, if you have type 1, type 2 code, you have here all the way of the code word is a multiple of 4, and we call it doubly even or type 2. I forgot to say that doubly even or type 2 code is the same. And the shadow is defined in this way. You have subcode of C0 here is the subcode of C, and C is type 1 code. And they prove that the way of the shadow, the enumerator of the shadow, is given by this formula. The first formula is given by Pierce-Gleason, the famous Pierce-Gleason theorem state about the way enumerator of linear code. Serial code, sorry. Not in general. Yeah. It's like, and in fact here is a way distribution of repetition code. No, maybe not. But here is some way enumerator of some serial code. So you can get the way enumerator of serial code with just these two guys. And the advantage of the shadow is to prove for non-existence of some serial code. And for my case, it will be useful for classification problem of the so-called extremal code, which hold some design. So when you work with coding, the favorite food is the humming distance. You cannot publish paper with bad humming distance. It's like if you can produce some linear code with humming distance larger than the previous known result, then your result can be published. But maybe it's hopeless because this maybe at the young level, maybe you cannot beat the result of other old people. And here you can follow. You can try to construct code which reach this upper bound. Yeah. And when the upper bound hold, then you call it extremal code. So this bound is for serial code, binary serial code. And a ternary is different situation, but I'm just talking about binary case here. Or just some example that I try to construct, or just it's not published because it's just show you some optimal code. That here we can construct a lot of, but just give some example that this construction is from orthogonal matrix. As I have just mentioned here, you just take one orthogonal matrix randomly, and then you test if you get something which have minimums like this. Then, in fact, I should say something about, but I need to access to internet. or maybe I will tell you later. In fact, there is a website that you can compare your result. If your result is the same, is as good as the database, I mean the data in the website, then it's okay. It will be better if you can get a better parameter than the previous known result. I mean the better parameter here, I refer to Hamming distance. If you can get a larger Hamming distance, then this is another direction. Here the number of cellular code is given by Perpustakaan. It's I mean you may know the author of fundamental. She wrote a book, Fundamental of Coding Series, something like that. Fundamental of Error Correcting Code, and you can explore many things in that book. Fundamental of Error Correcting Code by Perpustakaan, and even there are also open problems there. Now, the number of cellular code is given by these two cases. If type 1, you have the number of cellular code of length n here. Here, number of cellular code of length 2. And so the math formula will say if your classification, I mean when we talk about classification, it's like we try to distinguish those who are not equivalent. And equivalent here means that when you apply the permutation group, is it still in the same orbit or not? Here we apply the action group of permutation group on the cellular code. If the code is in the same orbit, then we say that this code equivalent to the other code in the orbit. And by some technique proof, you can get the number of cellular code look like this. You have here factorial of n, and here automorphism group of Cj, where J is the sum over non-equivalent code. So here, if you ask magma, then magma will provide you automorphism group. If you have code C, and you tie automorphism group, then magma will return you the automorphism group of C. Here we take the order of the automorphism group. And if you consider in the next section, I will talk about the classification of length 38. So here, the total number of non-equivalent cellular code of length 38 is this number. You can get this bound by considering here I mean the factorial of n, and then you take just you divide it by n factorial here. I mean you drop factorial n here, and then this I mean this term just 1 over something, right? So it is less than 1. So you can get if you drop the factorial here, you get the number of the lower bound of number of non-equivalent code. So here is much. I think it's 13 million is non-equivalent. but it's big. So you may not classify, or you can do it, but maybe it take more time. But maybe you can classify some interesting code, the one with the largest Hamming distance. And as you may see here, you can get the upper bound on the Hamming distance from this formula. So my first work is to classify serial code of length 38, but with the largest minimum distance. In this talk we will not consider the other Hamming distance, just the extremal one. So this is the algorithm. You start from a smaller code, then you extend it. Here you start from code of length. I mean, the goal is to get a code of length d+2, right? And you have to start from the code of length d. Here is represented by GD and GE. I will tell you why we have this decomposition. So if you want to get d+2, you have to start here from at least d. And when you extend 2 coordinate here, I mean, a code has a minimum distance d+2 if every code word here has at least minimum distance d+2, right? If the minimum distance here in the general analysis is less than d+2, then the code cannot have minimum distance d+2. So the idea is to start from smaller code and you apply recursive construction that you extend. In fact, you can extend something like 1, 1, 1, and here 0, 0, 0, or here 1, 1, 0, 0, because you can check that this is still self-orthogonal. But for complexity of classification, you need to have a clever idea that if you take here just maybe AI, then you will lose a lot of time. But if you have such a decomposition, then you can gain more time, because here the GD is the serial code of Hamming distance D, and when you extend 2 coordinate, the distance will be could be d+2, right? But if you don't have this decomposition, then you have to consider here, let's say AI or AI. Then if you look at the dimension here, when you consider length 38, the dimension here must be 19. Then you see you have to do all is just to search here, and 2 to the 19 you can calculate how much time that you spend. You have to try 2 to the 19 possible case. But if you have this decomposition, I mean, you cut in 2 blocks, and the first block is D, and second block is greater than d+2, I mean. So you can extend here, and what you get here, it could be here is not exactly d+2, but at least D. But This is just I want to get, but not expected to. In some cases, you can have only distance d. But if you want to get d plus 2, you have to reject all the one with the Hamming distance d. So I think this is just linear algebra and about matrix operation, and you can do it. You start from the small length. You decompose as two blocks. One is a subcode of Hamming distance d, and the other Hamming distance d plus 2. And then you extend the coordinate. And then you here you make direct sum with one dimensional. You take x as the last row here. Because here you go from length n to length n plus 2. But the dimension is still the same. Then for set-del code, the dimension is half of the length. So you can get search for one dimensional subcode, and you make direct sum. Here direct sum, I mean, so it's not in this subspace. Okay. So here you see we did some computation. In fact, the classification depends on I mean the subcode here. If you have here subcode of weight d with large dimension, you have very few choice for this, and it will make your program faster. Because you will have a very small possibility of AI, right? So here I calculate the dimension of the subcode. Here is the worst case, because you have only 2. I mean, dimension of the subcode is just 2. Then the rest will be 17. 2 to the 17 possibility. But when the dimension of the subcode increase, here you have only 2 possible choice. I mean, let's say here for the last case, you have only one component to be considered, either 1 1 or 0 0. But for the other, it's like you have to consider 0 0 1 1 0 0 2 to the n minus k. And if k is smaller, then the classification take longer. So here we calculate the and you can see that the classification go faster. That it takes just 3 weeks to get all the non-equivalent code. But maybe other people will take 3 months, 6 months. If you do not have such a decomposition, it's like you have to do all the it's just to search. And here our result of classification. We get something like 2,744. And later on, here we just classify distance 8. But for distance 6, distance 4, distance 2, we did not do it. As I mentioned here, it will here there are at least this number of non-equivalent, and you have to you must have a very powerful computer, because you need to compare the equivalent. It's like you have equivalent test, and you also need a memory space for storing. And in fact, for length 38, the classification was done by Harada and Munimasa also for all length. But for us, we only classify the higher distance, and it took just 3 weeks with my small computer, and we can get the result. Normally, when you do classification, you need something like a powerful computer, parallel programming. It's like you need maybe 100 computer in parallel, and you do computation. And the classification will take not a very short time, but normally it's like months or year. Then you need to find a clever idea. In fact, I haven't checked if length 42 already classified or not, but this is just like the classification by Bujuk and Harada. And in fact, they just do exhaustive search, and I think it take a lot of time. So from the classification of length 38, we would like to have classification of S-estimol that I have just introduced. Here, estimol, it means attain this bound. But there is also the notion of S-estimol. When the code whole design, then there is also the notion of S-estimol, and we want to know how many S-estimol and equivalent code. Maybe I should say something about self-dual code. In fact, self-dual code has many applications, maybe secret sharing. Then you need to know the weight distribution. That's why we do classification. As I said, that when you have you classify, then you will get some weight distribution of non-equivalent code. Then people can just use this code to apply in cryptography. I mean, maybe secret sharing scheme or other combinatorial object for computer science. So for this code, you have 2 parameters, this kind of code, and the upper bound was given by Bychok and Galbraith. This is my code also for classification of length 38. This is the upper bound for the estimol. You have 2 situations here. So we call it S-estimol when the upper bound attained. So if you apply here n equal 38, and I mean here you can get some upper bound. Then I think for length 38, you can check all these parameters, but the smaller parameter was already done by Galbraith, except for d equals 6 and d equals 8. Here you see that there is also information about T design, that if you consider the code word here, it will hold T design, to design here. And here the same. Here we prove some result that make our classification faster. Normally, before proving this result, we try to do some, let's say, the recursive construction, but it takes very long time, and then it may have been hopeless. But we try to think about the shadow. As I mentioned, I mean, some code exists if the shadow also exists. So we get the information from the shadow to classify, I mean, this code, and this the key theorem. I mean, in the first construction, we start from the smaller length, and we reach the larger length, right? But here is the reverse. You start from the larger length, you subtract 2 coordinates, and then you get a smaller code. Here there are 2 possible classifications. Either you start from the smaller one, the smaller length, to length 38, or you start from the length 40 and you subtract 2 coordinates to get length 38. But in this case, you must consider what kind of what parameter of length 40 you have to consider. And on the shadow, we can say what parameter you need. So here the important theorem that you start from this length with shadow over S, then you get something shorter, and the shadow must have a way like this. So you have to consider just a shadow with some certain way, and as I show you here, the way of the shadow is also determined by Conway-Sloan. Yeah, the way of the shadow. Then you can calculate, you give parameter, then you will have information of the way of the shadow. So as I said here, if you apply the way numerator on the shadow, you get some information like this. It means that if you want to classify the shadow code with shadow weight 6, you have to start here from 7. When you subtract coordinate, then the shadow will decrease by 1, so you get 6, right? And here's the same. But from the classification of Harada, we get some code with this shadow, so we can get the information from the shadow to classify, and then you see here it runs faster than the classification from the smaller length. If you start from the smaller length, maybe it took year, I don't know, because I tried maybe 1 week, it returned me nothing, and then we try to modify. It just take maybe less than 10 minutes to get all. So here is the first one can be reachable by the classification of yes, can be obtained by oh no here I mean from Harada, that we use the subtraction procedure. Here the first case there are only 2, and the second one we have 1730. And for length, we have other length. But maybe there are some work to be done for length 42. But you cannot apply our method, but you have to modify in order to classify this this length. I haven't checked if this is already done or not. But here we are just talking about as estimol. But if you have the classification of this length, then you can get as estimol by checking the Bicok-Gabbrit bound. Here, the non-result as you see here, there are only two. So the complete here is the complete classification. But for other length, if you check the Bicok-Gabbrit bound, it doesn't have. I mean, there is no small after length 44 of minimum distance 6. But here, you see, as I should update it, but I'm sorry, there may be some new result here. Here there are some construction, but it's not classification. The next session will be the general, orthogonal group in arbitrary field. But I'm not sure if you want to take a break now and come back later. To spend or want to have a break or let's have a break. Because it's like this, we'll be introducing, so just maybe 10 minutes is not enough. You have any question? Comment? For research or for PhD student, sometimes the classification work is valuable. And not just code, but maybe some other object like graph or yes. But the maybe only code over finite field can be easily classified, but maybe over ring is not so easy. You have complicated structure and yeah. So if you don't have any question or comment, maybe we have a break and come back. And the next session will be mine again. Don't be worried. We can.
Please give applause to Mr. Lin Sok. Okay. We will now have a break for coffee break in. Okay, you can go to front desk and have coffee break, boss.